Okay, so now we're into chapter 6, lecture on probability. Uh, in the real world, when we talk about the likelihood of something happening, this is sometimes expressed as a fraction or a percent. But in this class, when we talk about probability, we're not going to be dealing with fractions. If you were asked to report a probability, what you should be doing is reporting a decimal with 4 places, right? We talked about this all the way back in chapter 2 when we were making frequency distribution tables and we were figuring out the probabilities of certain scores. So this means that your probability is going to fall within a range of 0 to 1, right? It can't be less than that. It can't exceed that. And again, just to reiterate, if you remember our frequency table work in chapter 2, we express this probability as a proportion. So let's say we had a fair 6-sided dice, right? That means that you have an equal probability of rolling any digit 1 through 6. Well, what's the probability that we would roll a 7? How would we figure that out? Well, the formula, as you can see, is right there on the slide. It's the number of outcomes favoring A, right? So the probability of A, probability of something happening, in this case, probability of rolling a 7. So the number of outcomes favoring rolling a 7 divided by the total number of all possible outcomes. Well, the number of outcomes favoring a 7 is 0, right? Because the die only goes all the way up to 6. And the total number of possible outcomes is 6, right? You can have a 1, you can roll a 1, 2, 3, 4, 5, or 6, right? So there's 6 possible outcomes. So 0 divided by 6 is going to give us a probability of 0.0000, or just 0. But remember, we'd report it out to 4 places. What's the probability of rolling any number 1 through 6? Well, the number of outcomes on any given roll, right? The probability of rolling a 1 through 6. The number of outcomes where on any given roll we can roll 1 through a 6 is 6, right? Because that should make common sense. If we divide that by the total number of possible outcomes, which is also 6, but we get a probability of a perfect 1, right? Or 1.0000. What's the probability that we would roll an even number? Well, first of all, how many even numbers are there on a 6-sided die? There's 3, right? 2, 4, and 6 are the only possible outcomes that favor rolling an even number. And again, if we divide that by the total number of all possible outcomes, 3 divided by 6, that's a probability of 0.5000. Now, for the definition and formula of probability to be accurate, the outcomes that we're talking about can't have any bias. So, for example, this die in particular can have bias, right? So think about it for a second. What do you think the difference between this die that you would get like in a board game compared to these type of dice that you would find, say, at a casino? Well, for one thing, the gambling dice, the red dice, they have very sharp edges. The spots are painted on, right? They're perfectly weighted and balanced. Whereas this sort of game die has rounded edges. Each of these dots is sort of indented. In fact, a very skilled person with good dexterity can learn how to roll this die so that they can manipulate the outcome. Certainly not perfectly, but they can learn how to roll it so that they have a greater probability of rolling a specific value. Whereas these particular dice are designed to be totally random, right? So in other words, this has a bias that these don't, right? So if we're trying to sort of judge the probability of this die, well, the problem is this can be manipulated, right? And so in order for probability to be effective, right? In order for the idea of probability to actually work, then there can't be any sort of bias. So because probability requires situations where there's no bias, as a consequence, at least when we're thinking in terms of science and psychology, probability requires that we have a random sample of people, right, or participants in our study. And I want to note that this is different from random assignment that we spoke about earlier in the semester, right? So random assignment requires each individual in a sample that you're using for your experiment to have an equal chance of being placed in either the experimental group or the control condition. What we mean by random sampling is that any individual in our population has an equal probability of being selected to participate in our study, right? So, imagine our class here, our online class. There are probably several online classes going on at the university at any given time. I'm not sure how many. Let's just say for the sake of argument, there are 7 different sections of online statistics being offered at the university. Is our particular class a random sample? No, it isn't, right? If we just treated our class as a random sample of all students at the university, well, that's not really the case, because most of the people in our class are psychology majors. You've selected to take this particular class at this particular semester, so there's a little bit of self-selection bias that affects the makeup of our particular sample. But let's say we were interested in all of the possible students at the university, right? And we send out a survey to 80 random students to their email addresses. Well, that would be a better example of randomly sampling. So we couldn't use our class as an example of a random sample of all the students at a university. But if we randomly selected 80 email addresses and asked them to participate in some experiment we were running, that's a better example of random sampling. And in this case, any student at the university has an equal chance of being selected for our study, as opposed to just using students in our online class as potential participants for our study, right? Okay, so random sampling can be done with or without replacement. Typically in psychology, it's done without replacement, but I'm going to explain both of them anyway. So sampling with replacement would be like, let's say you want to find the probability of some event where, maybe you're selecting lottery balls or something like that, and the numbers are between 1 and 60. And so you pull a number from the hopper, right? And whatever it is, you read it off, you record it, and then you put it back in the hopper before you select the next number, right? So that would be sampling with replacements. So you select a sample from the population, and then you put it back in before you select again, right? And as a consequence, the probability that I draw any particular number, right, in this case, if we're talking about lottery balls, is going to remain constant on every single draw, right? Conversely, if I'm sampling without replacement, then I'd select the ball out of the machine. I would not put it back in the machine before I select the next number. And if I kept doing this, I would change my odds every time I select a new ball from the machine. I'll give you another example here of sampling with replacement, sort of using a deck of cards as an example here. And I'll do the same thing for sampling without replacement. Again, I want to reiterate, typically when we're talking about running an experiment, typically what we engage in is sampling without replacement. But let's first talk about sampling with replacement. Let's use a deck of cards as our example. There are 52 cards in a deck, not including the jokers. There are 26 red cards and 26 black cards. There are a total of 4 suits, right? Hearts, clubs, and spades. And there are 13 cards in each suit. And remember our formula for determining probability. It's the number of outcomes that favor a scenario divided by the total number of possible outcomes. So what would be the probability, right? What would be the probability of drawing a red card? Well, as I stated, half the cards in the deck are all red, right? So that means 26 cards are red. So 26 cards would meet our criteria of drawing a red card. If we divide that by all of the cards in the deck, which is 52, our answer is 0.5000. Okay, so again, we're talking about sampling with replacement. So let's say we put that red card back in the deck, right? And now we want to draw another card. Let's ask ourselves, what is the probability of drawing an ace? Okay, well, how many aces are there in the deck? 1, 2, 3, 4. So that's the number of possible outcomes that favor drawing an ace, divided by all the possible number of outcomes, which is 52. So we'd be dividing 4 by 52. And the probability of drawing an ace would be 0.0769. Okay, again, we're going to put that card back in the deck before we draw the next card. And we're going to ask ourselves, what is the probability of drawing any club card or a 7, right? Any club card or a 7. Okay. So, first of all, how many club cards do we have? 13. And in addition to that, how many sevens? So, well, there's one seven within the suite of clubs, so that's already included in here. There's a seven of hearts, a seven of spades, and a seven of diamonds. So 13 clubs, 14, 15, 16, right? So the number of outcomes that favor drawing any club or seven is 16. We're going to divide that by, again, the total number of all possible outcomes, which is 52. So the probability of drawing a club or a seven is 0.3076. 0.3076. Now, in each one of those instances, every time I drew a card, I put the card back in the deck. So my odds didn't really change. My odds only changed depending upon maybe what card I was hoping to draw, for example. But my odds always stayed the same. It was always 52 in the denominator of this particular formula. All right, so let's talk about sampling without replacement. So in this case, every time we sample, we're not going to put the card back in the deck before we draw again. And again, this is much like what we would experience in running an experiment. Typically, you sample from a population, right? So you select somebody at random from your population. And once you run them in your experiment, you typically don't run them again, right? You don't sort of, in a sense, put them back in the population and then have a chance of selecting them to participate in your study again. So typically in psychology and in science, we're sampling without replacement. All right, so let's pretend on a previous draw we drew a two of clubs, right? But in this case, we don't want to put it back. We're going to leave it out of the deck. On my next draw, what's the probability of drawing another club? Well, as we established, there's 13 club cards in the deck, right? Well, we drew a club card on the previous draw. We're not putting it back. So that leaves 12 club cards left, right? Because we drew a two of clubs on that last draw. It's out of the deck. So the only other club cards that remain are these, right? 3 through ace. But also because we've taken a card out of the deck, it changes the denominator of our formula, right? Before we had 52 possible outcomes, but now we have 51 possible outcomes. So the probability that we're going to draw any club, we would figure that out by dividing 12 by 51. And the probability of that is 0.2352. Okay? So we've drawn a two of clubs, and say on our second draw was another club. So let's say on that last draw we drew a five of clubs. And again, we didn't put either card back in the deck. What is the probability on the next draw we'd select a queen of hearts? Okay. Well, we're down two clubs, right? But how many queen of hearts do we have? Well, we only have one, right? There's only one queen of hearts in the deck. But remember, we're down two cards overall in the deck, right? So what's the denominator in our formula now? It becomes 50, right? We started with 52 cards. We drew a two of clubs, didn't put it back. On the next draw, we drew a five of clubs, didn't put it back. So now we're down to 50 cards. The only possible outcome that favors drawing a queen of hearts is 1. So to figure out the probability, we would divide 1 by 50. We'd get a probability of drawing a queen of hearts as being 0.0200. So as you can see here, the effect of sampling without replacement means that your odds change dramatically every time you select another, in this case, card. But you can think about it the same way in terms of selecting people to participate in your study. Okay. So probability is related to the normal distribution. Like just, we're not talking about this for fun. There's sort of a method to my madness here. And remember, we've talked a little bit about normal distributions now. Remember that they're symmetrical, or, we think about them as being close to symmetrical, right? So 50% of all of the scores fall above the mean. And if we were to add up the percentages, right, from 0 to 1 standard deviation, that's 34.13% of all the observations under the normal distribution. From +1 to +2 standard deviations, that's 13.59%. And then beyond 2 standard deviations of the mean all the way to the end of the distribution, it's 2.28%. So if we were to add all of these up, right, we would get 50%. And likewise, 50% of all scores fall below the mean, right? So 50% fall above the mean, 50% fall below the mean. Most scores fall close to the mean. Here I'm showing you, within -2 to +2 standard deviations. That's going to represent about 95% of all of our scores. So almost all of our scores fall within 2 standard deviations plus or minus of the mean. Fewer, more extreme scores fall out into the tails of the distribution. Roughly around 5% of all of our observations should fall into the tails of the distribution. So again, sort of to reiterate here, more specifically, right, in a normal distribution, you get 34% and some change of our scores between the mean and 1 standard deviation, 13.59 between 1 and 2 standard deviations, and again, 2.28 falling beyond 2 standard deviations above the mean. And of course, the same is true for below the mean, right? So you would get, because it's a symmetrical distribution, if 34.13% of all of our scores should fall between 0 and +1 standard deviations above the mean, well, then because this is symmetrical, 34.13% of all of our scores should fall between 0 and -1 standard deviations from the mean. Same thing, 13.59% should fall between -1 to -2, and so on. Now here, we're talking about these as percents, right? But we could just as easily, and probably should, describe them as proportions, right? So remember, it's very easy to convert percents into proportions. You just simply move the decimal point 2 places to the left. So the probability of any value falling between 0 and 1 standard deviation would be a probability of 0.3413, right? The probability of anything falling between 1 and 2 standard deviations of the mean would be 0.1359. And then the probability of everything beneath the curve is an even 1, right? 1.000, because every single one of our scores, 100% of all of our scores, falls within the entirety of the curve, right? So the probability in this case would be 1.000. Okay. Let's do some math. We're going to start off with some pretty easy math here. It's going to get a little bit more complicated, but not too bad. And this is really going to illustrate the relationship between probability and the normal distribution. So here I've got a distribution for the age at which babies learn to crawl, with a mean of 35 weeks and a standard deviation of 3 weeks. In reality, in the real world, the distribution for crawling age is actually slightly negatively skewed, but for our example here, we're just going to pretend it's normal. So on average, babies start crawling around 35 weeks with a standard deviation of 3 weeks. Now imagine we have 100 babies, right? We've computed, we've got the age at which each and every one of these babies learned how to crawl, and we've went ahead and we've computed z-scores for all 100 of our babies, right? So for each baby, we would take the time at which it learned how to crawl, subtract out of that 35 weeks, and then whatever that difference is divided by 3, and we would do this for every single baby, and it would give us a z-score, right? A z-score for all of our babies, for one of our babies, but we could do it for all of them, is my point. Now, if we were to pick one baby at random out of this group of 100 babies, well, what would be the most likely z-score that we would get? Well, technically, the most likely z-score we're to get is 0, right? Because that's the mean. But anything between -1 and +1 would be pretty common. We can feel really confident in saying we'll get something between -2 and +2, for example, right? But we could be a little bit more specific here, right? And we could ask, what proportion of babies should fall between the mean and 1 standard deviation of the mean? Go ahead and it's pretty easy to figure out, but take a beat here and see if you can figure out yourself. Pause the video and I'll show you the answer on the next slide. Yeah, it's pretty easy, right? You should have looked at the percentage, right? Looked at the fact that we were trying to sort of see what proportions of the babies would fall between the mean and +1 standard deviation of the mean. We already have the percentage listed there as 34.13. If we convert that to a proportion, the proportion is 0.3413. Let's see. What proportion of babies should fall between -1 and +1 standard deviations of the mean? Well, again, it should be pretty easy to figure out, right? If 34.13% fall between 0 and +1, and we're asking, well, what's the proportion that falls between -1 and +1? Then we just simply add these together, right? Move the decimal place, add these percentages together, move the decimal place over 2 places to the left, right? And we get a proportion of 0.6826. So a proportion of 0.6826 of all babies should fall between -1 and 1 standard deviation of the mean. All right, so let's move away from proportions for just a second and ask, well, what does this mean in the real world? If we sampled 100 babies, roughly how many babies, like the number of babies, should fall between -1 and +1 standard deviations of the mean? Well, how might I figure that out? I could take my sample size, right, which is 100, and I can multiply it by that particular proportion, right? And it would tell me exactly how many babies should fall between those two values based on the sample size and the proportion. So how would I get that? Well, I've already figured out that it should be a proportion of 0.6826 of all babies that fall between -1 and +1. So if I take my sample size and multiply it by that proportion, I get a value of 68.26. But we're talking about babies, so this is discrete data, not continuous data, so we want to round it appropriately. So it would be appropriate to round down, and we would predict that 68 of our 100 babies should learn to crawl somewhere between -1 and +1 standard deviations of the mean. How many babies might be in the extreme? This is wrong. It would be 5, right? Why? Because the extremes are anything above 2 standard deviations or below -2 standard deviations. And we know here that represents 2.28%, right? These values that are in the tail. So again, we can convert it to a percentage, and we have to add both of these tails together, right? So this 0.0228 is the proportion in this tail. This 0.0228 is the proportion in this tail. And if we add it up, we get a proportion of 0.0456. If we take our sample size and multiply it by that proportion, right, we get a value of 4.66. But again, we're talking about the number of babies, so we would round that appropriately. In this case, we would round up. And we might expect 5 babies to be in the extremes, right? 5 babies to end up in the tails. So 5 babies to be 2 standard deviations above the mean. Well, not 5, but it's a total of 5 would be either 2 standard deviations above or 2 standard deviations below. Okay. Now, what proportion of babies should learn to crawl after 41 weeks? Now, here we need to start figuring out some z-scores, right? We can't just we could eyeball the table, but I want to sort of start easy here, kind of start simply by calculating a fairly easy z-score, sort of figuring out how to figure out how to find the proportion here. So what we're asking is, what proportion learn to crawl after 41 weeks? So the first thing we need to do is compute a z-score, right? And we're going to treat this 41 as the raw score, right? So we're going to go 41 minus 35, whatever that deviation is, we're going to divide that by 3, right? So again, if you were doing this problem in the homework, you'd want to show your formula. And here's the math, right? 41 minus 35 is 6. If we divide that by the standard deviation of 3, we get a z-score of plus 2.00. So, and that's the easy part. Here's where it gets a little tricky, right? We want to find the proportion that learn after 41 weeks. So let's go back to this slide here. Imagine, right, so we figured out that our z-score was plus 2.00. So what we would want to do is draw a normal distribution like what you see here. We've been doing that for a while, right? We'd want to label where that is, right? And it plus 2.00 standard deviations is here. And the question is asking us is what proportion learn to crawl after 41 weeks? And this is where it gets tricky. When you're trying to figure out that proportion, you have to ask yourself, am I trying to find the values to the right of the mark that I put through the distribution, or am I trying to find the values that are to the left? Well, the fact that this is asking us to find the proportion after 41 weeks suggests that we need to find that z-score and find whatever proportion of scores is above that z-score. Hopefully that idea makes sense to you, right? And here's how it would work, right? So remember, we would plot where our z-score fits into a normal distribution. And because we've already gotten our little example here, all the little percentages laid out, and it's quite easy for us to convert these into proportions, well, we can see that the percentage of babies that should be above 2.00 is 2.28%. If we convert that to a proportion, then we can see that the proportion of babies that learn to crawl after 41 weeks would be 0.0228. Let's try another one. What proportion learn before 32 weeks? So again, the first thing we need to do here is compute a z-score. Then we need to draw a normal curve. We need to mark where our z-score is in that curve, and then figure out which area of the curve we should be looking at to find the proportion of scores. So go ahead and try and compute that z-score. In fact, try and do the whole thing yourself here. Try and figure out this whole problem. So go ahead and pause the video. So figure out the z-score, draw your normal curve, plot where your z-score that you compute should be, and then think about all these percentages, right? Think about how these percentages relate to distances between these curves, and see if you can figure out, based on this problem, what proportion of babies should learn to crawl before 32 weeks. Okay, so here's the math, right? 32, which is our raw score, minus 35, which is our mean, is going to give us negative 3. We divide that by 3, and that gives us a z-score of negative 1.00. And so I plot that in my distribution. It's right here, right? Negative 1.00. And it's asking me what proportion learned before 32 weeks. Well, what I want to do is find, okay, what proportion is between negative 1 and negative 2, and then what proportion is beyond negative 2. And I want to add those up. That will give me my proportion of babies that learn to crawl before 32 weeks. And again, in this example, because we're working with very simple z-scores here, right, a z-score that's exactly negative 1.0, we can look at the other side of our figure here and see what percentages relate to these symmetrical areas of the curve. Well, the percentage between negative 1 and negative 2 is going to be the same percentage between positive 1 and positive 2, which is 13.59. And then the percentage from negative 2 to the end of the distribution is the same as the percentage for positive 2 to the end of the distribution, which is 2.28. As you can see here, I've already converted them both into proportions, and I've added them up. So the proportion of babies that should learn to crawl before 32 weeks comes out to be 0.1587. And that's everything under the curve here at this particular area, right? The proportion between negative 1 and negative 2, and the proportion between negative 2 to the end of the distribution. Okay. So the fact that we know what proportion of people are likely to fall within each section of a normal distribution, this may seem a little silly or trivial, but it's actually the foundation for inferential statistics. It's the foundation for many of the tests that we're going to talk about in the following chapters. Remember, the purpose of inferential statistics is to use a sample to draw conclusions about a population. So the proportions that we've been talking about so far, they're helpful, right? But so far we've been describing our normal distribution very, very generally, right? They only refer to, a couple of z-scores, and we're going to need to be much more precise when we move into inferential statistics, right? Everything we've been doing, our z-scores are landing perfectly on negative 1.00 or perfectly on plus 2.00. In the real world, that doesn't typically happen, right? You get a z-score of negative 1.37, for example, and you still might be interested in determining what proportion might learn to crawl before or after, right? So imagine our z-score sort of fell in here, right? Well, it's sort of tough to look at the percentages of this distribution and figure out with any degree of precision, what proportion might learn to crawl before 32 weeks. Well, the good news for us is that we can be more precise, and we're going to use a tool to help us be more precise called the unit normal table, and it's going to make things very easy for us. And so at this particular point in lecture, I'd also say you want to have your book with you really for every remaining class, now that I think about it, because we're always going to be, almost always, going to be looking up values in a table for us to use in the answers to our questions. So if you look in your book to the Appendix B, I think it's page 647 in this edition, you're going to find that we're going to be using this table to do a couple things. One, to find z-scores and find their associated proportions, right? Depending upon which area of the curve we're looking at. We will also be looking up proportions and trying to find the corresponding z-score, right? But let me just sort of walk you through kind of the basics of this table. You've got 4 columns. In the first column, you have the z-scores. They start at 0, and they work their way all the way up to 4. And you'll note that there are several pages of ascending z-scores, right? This is a fairly long table. So again, the z-scores go from 0 to 4. Then we have 3 separate columns that describe the proportion of scores in different areas of the distribution. Now, for any z-score that you compute, you can draw a normal distribution, and you can draw a vertical line through the distribution and break it into different areas, right? Much like we were doing with the baby crawling data, right? And much like what you see here, right, in any of these different examples. And each area, right, each area is associated with a specific proportion that can be found in the unit normal table. So let's pretend we had a positive z-score like you see here, right? Maybe this was plus 1.00 again, right? Maybe this was that score. If we wanted to see all the scores at or below a z-score of plus 1.00, right? So that means all the scores that fall from here all the way to the end of the distribution. We would look in the column that says proportion in body, right? Column B. Let's say we had the same z-score here again, right? But instead of looking for the proportion of scores that fall at or below that z-score, if we were looking for the proportion of scores that fell at or above, right? So from that score all the way on the right side, the remainder of the distribution, right? We would look for the proportion in the tail in column C. And there may be instances where we have a z-score, like let's say we have again a z-score of plus 1.00, and we're interested in the proportion of scores that fall between the mean and that particular z-score. Then we would look in the column D, proportion between mean and z. So this is some sort of just general things to sort of remember. This is why drawing out these normal curves on your homework is very important, right? Because when you're answering the homework questions, you're going to compute at least one z-score. You're going to mark where that z-score falls within a normal curve, right? Within a normal distribution. And in many instances, you're going to need to determine whether you need to find the proportion of scores below that z-score or the proportion of scores above that z-score. And depending upon that answer, well, that's how you're going to know whether to find the proportions in columns A, B, or C, right? Another thing I want to draw your attention to is that the z-scores in the table, they're absolute values because the normal distribution is symmetrical, right? So a z-score of plus 0.31 is essentially the same as a z-score of negative 0.31, right? The proportion of scores that would fall between the mean and plus 0.31 is the same as the proportion that would fall between the mean and negative 0.31. Why? Because this distribution is symmetrical, right? So if you fold it in half, here, let's go back to this old slide, right? If you fold it in half, you'd have equal amounts on each, right? 50% to one side, 50% to the other. Again, note how the proportion of scores between 0 and plus 1 is the same as 0 and negative 1, right? So same is true with the table. The proportion between 0 and plus 0.31 would be 0.1217, whereas the same is true for the proportion between mean and negative 0.31. That would also be 0.1217, right? because it is a normal symmetrical distribution. So all of the z-scores in the table are treated as absolute values. You'll have to keep that in mind when you're looking at z-scores in the table. Again, this illustrates exactly why it's so important to sketch a normal distribution and appropriately label your z-score. Now, z-scores can be positive or negative, but these proportions are always going to be positive, right? So again, we already determined that the proportion of scores between the mean and 0.31 is 0.1217, as well as the proportion of scores between the mean and negative 0.31. It's also 0.1217. It wouldn't be negative 0.1217. It would just also be 0.1217. So be careful about that. Okay, so let's do a little bit of practice here, and hopefully this will become a little bit more intuitive. Let's say we have a z-score of plus 1.00, and we want to know the proportion of scores that fall in the body, right? So in other words, so we want to know the proportion of scores that fall at or below our z-score of 1.00. So in other words, all the scores from the leftmost point of our distribution all the way up to a z-score of plus 1.00. Well, what column do you think we'd look at? Hopefully you said the body, right? Hopefully you said the body, because we're looking for all of these scores. And if you go back to our image here, right, if you're looking for a positive z-score, for all the scores for a positive z-score at or below, it's going to be a whole mess of scores here. It's going to be a big area. We call that the body. And the proportion of scores that fall at or below a z-score of 1.00 would be a proportion of 0.8413, right? So there it is. I'd label my z-score on my distribution, and I'd label the proportion. Okay. What if we wanted to know the proportion of scores that fall at or above a z-score of plus 1.38? Do you think that we'd look in the body? Do you think that we'd look in the tail? Or do you think that we'd look in the mean to z column? Well, here's some proportions right here. Here's our z-score, right? So the first thing we want to do is locate our z-score of 1.38. Then we have to determine whether or not we're looking in B, C, or D, right? Body, tail, or mean to z. Again, we're looking for the proportion of scores that fall at or above the z-score of plus 1.38. The proportion would be 0.0838, and we would look in the column for the tail, right? Because we want to know the proportion of the scores that fall at or above that particular z-score. So there it is, right? We would label it in the normal distribution, and we would label the proportions. All right, let's say we have a z-score of negative 0.87, right? And we want to know the proportion of scores that fall between the z-score of negative 0.87 and the z-score of 0, right? 0. Which column would we look in to figure that out? Well, first, and this gets it's not too tricky, but you can't forget that these are absolute values, right? So the z-score we're looking for is negative 0.87. But as you see, there is no such thing as negative 0.87 in the table. But remember, because our distribution is symmetrical, we can treat these as absolute values. So the z-score we're looking for, even though in the reality it's negative 0.87, the z-score we're looking for in the table is 0.87. And if we're looking at the proportion between the z-score of negative 0.87 and a z-score of 0, that's just another way of saying that we're looking for the proportion between mean and z, right? And so the proportion in that case, it's not negative 0.3078, it's simply 0.3078. See, it's not negative. The proportion of scores that fall between 0 and negative 0.87 would be the exact same proportion that were to fall between 0 and plus 0.87, and it happens to be 0.3087 of our score should fall between these two values, right? So again, the column that you use is dependent upon whether you're looking for scores above or below a specific z value. Some of it depends upon, of course, whether your z-score is a positive or a negative. Because here, for example, for a positive, let's say again, this is plus 1.00. If we're looking for the proportion of scores at or below this z-score, we would look in the body. But what if we had a z-score of negative 1.00 and we were looking for the proportion of scores that fell at or below negative 1.00? Well, we'd be looking for a much smaller area, right? We'd be looking in the tail, right? So in that case, we'd look in the tail column. So it depends again on what area you're looking for, and it depends again on whether or not your z-score is a positive score or a negative score. And again, just a reminder, these are absolute values, right? So because the distribution is symmetrical, you don't have to worry about finding a negative value in the table. Whatever it is for the positive value, it'll be the same thing as if it were a negative z-score. And then don't forget that our proportions are always positive. Okay. Let's say I want to find the proportion of scores below a z-score of negative 2.03. What column would I look in? Would I look in the body? Well, that says the proportion is 0.9788. Well, let's look at our figure again. I know that the entire distribution has a proportion of 1.0000, right? So a proportion of 0.9788 is awfully close to the entire distribution, right? If I'm looking for the proportion at or below this value, just by eyeballing it, I don't think 0.9788 of all of our scores fall below at or below negative 2.03. Seems more likely that those scores would fall in the tail, right? Which shows a proportion of 0.0212, right? So that makes sense. So again, I just want to reiterate, you have to take a little bit of time, particularly early on as you're learning how to do this. Don't just rush through to sort of figure this out. Make sure that you've computed the the Z score correctly. You'll make sure you've correctly labeled where that z-score is in the normal distribution, and make sure you understand exactly what area of the distribution the problem is asking you to find a proportion for. And if you're careful there, then you shouldn't make any sort of unnecessary mistakes. So again, sketch the curve, label the known scores and proportions, right? Remember what it is you're looking for, right? Are you looking for a proportion, right? If you are, then in this case, is it in the body, the tail, or is it in mean the z? Sometimes we might be working backwards and trying to plot raw values, which we'll talk about in a little bit. So you just want to make sure that you label everything correctly. And then you use that unit normal table in order to find what the proportion is that fall in the area that you're looking for. All right, so let's talk about a few examples here. Finding probabilities for specific z or x scores, and then finding the z or x scores associated with specific probabilities. Let's see, I'm going to skip this. This is something I don't even cover in the homework, and so we're not going to do that. But we're still going to deal with the probabilities here. And before we get into it, I want to really illustrate why this is important. Probability is the foundation of inferential statistics, right? Which is something I said already, but it's worth repeating. It links samples to populations. So ever since we started computing z-scores in Chapter 5, the situations we've been talking about have involved converting a single raw score into a z-score, and then now we're talking about finding the probability of a person falling above or below that score, or in between that score and another score. But when we get past learning these things, we get into real research, we're rarely talking about a single score. Like typically we're now sort of shifting gears into talking about the mean for a sample, right? The mean of several scores. So imagine that we're interested in whether a medication that's commonly given to infants who suffer from certain types of respiratory illnesses, whether that medication impacts the age at which they learn to crawl. Now, maybe this medicine is very effective at treating the illness, but we're worried that it might have some negative effects on motor development. So to test this, we wouldn't just give the medication to one infant, right? We would take a random sample of infants. We would give them the medication. We'd probably have another group that gets a placebo, right? We look at the mean crawling age. Let's say the mean for the sample of say 40 infants who took the medication is 38 weeks, right? So on average, these children who took the medication learned to crawl, right? The sample of children learned to crawl at 38 weeks. Now, we don't even actually have to have a control group in this scenario, right? We could then determine whether this mean, right, this mean of 38 out of a sample of 40 infants, whether or not this mean is likely or unlikely given the national average, right, the data we were working with earlier, that's 35 weeks, right? And this would help us decide whether that medication has a negative impact on motor development or not, right? So, in other words, we can get a sample of 40 babies, give them our medication, and test them, run a statistical test on their data in comparison to what we know about the data in the population. So, this would still involve things like z-scores. It would involve the unit normal table, but it's a little bit different than what we've discussed here because now we're dealing with the sample mean rather than a single raw score. And this is something that we're going to talk about when we move on to chapter 7. So I'm sort of just doing a little bit of foreshadowing here, but for now, we're going to stick with finding proportions and probabilities and or percentages for one score within a distribution. And so let's do a problem here. Some of you might be familiar with this particular instrument here, the Reynolds Adolescent Depression Scale, or the RADS. So it's a 30-question survey instrument, and it's designed to assess depressive symptoms in adolescents aged 13 to 18. And the scores on each of the 30 questions in this particular inventory range between 1 and 4. So what you get when you sum up each participant's total scores, you're going to get a range of 30 on the absolute lowest to 120 on the maximum. And I should also stress that the purpose of this particular scale isn't to diagnose adolescents with a particular disorder or diagnose them as having depression. Rather, it's to assess the symptoms to determine whether they are at risk for developing depression. And so the way this works is that any kid that scores a 77 or higher is at risk for developing depression. All right, so we have some data here from the population, right? Because, and again, we obviously haven't measured every single kid in the world, right? But so I'm using some sample data here, and I'm just pretending that it's population data. Although we've certainly been running this particular inventory for many years, and I think we probably have a good sense of really what we might be able to predict what that population data would be. But for the sake of our example, we're going to pretend that the population mean is 60 and the population standard deviation is 14. And so what we're asking here is what percent of adolescents are at risk for developing depression? What we're really asking is what percent, right, given this mean and standard deviation, what percent would score a 77 or higher? So I want you to pause the video and try and answer this question, and I'll show you how I answered it when you come back. All right. Well, first thing we want to do is figure out the z-score for 77, right? Because, again, let me go back to this. What percent of adolescents are at risk is the same question as asking what percent of adolescents should get a 77 or higher, given that the mean of the instrument is 60 and the standard deviation is 14. So 77 minus 60 is 17. If we divide that by the standard deviation of 14, we get a z-score of plus 1.21. So it's asking what percent of adolescents are at risk. Well, the percent of adolescents at risk are anybody that gets a 77 or higher. So if we plot the z-score that we computed of plus 1.21, this z-score of plus 1.21 is nothing more than a standardized score of 77, given a population mean of 60 and a standard deviation of 14. So if we're asking the proportion of kids that would get a 77 or higher, we're asking what proportion of kids should be at or above a z-score of 1.21. So the question here is to find that proportion, which we'll ultimately use to convert to a percent. Are we looking above? Are we looking in the tail? Are we looking in the body? Are we looking at mean to z? Well, it should be pretty obvious if we're looking for the proportion at or above a z-score of plus 1.21. We are looking in the tail, right? So we find our z-score of 1.21. We go over to find the proportion of scores in the tail. That's 0.1131, right? 0.1131. And remember, the problem is asking us what percentage of adolescents should be at risk. So we can convert that actually to a percent by moving the decimal point 2 places to the right, and we get a percentage of 11.31. So given these data in the population, right, given that the mean score is 60 with a standard deviation of 14, and 77 is the cutoff score that are at risk for depression, we would expect any kid between the age of 13 to 18, 11.31% of them should score 77 or higher, and as a consequence, should be at risk for developing depression. Okay. Now the next question we're asking is, let's say we run a school of 250 students. How many of our students should be at risk? In other words, if we were to give this exam, right, this instrument to 250 kids between the ages of 13 to 18, how many of them should score 77 or higher? I'll give you a hint. We played around with this idea when we were working with our baby data. So go ahead and pause the video, see if you can figure this out. Okay. Remember, what we're going to do is multiply our sample size by our proportion, right? Well, our proportion of students at risk should be a proportion of 0.1131. We already figured that out in the previous step. And we can multiply that by our sample size, right? We have 250 kids in our school, and we get a answer of 28.27. But again, we're dealing with discrete data here, right? Children are discrete data, not continuous data. So it makes sense to round that value to 28, right? 28 students out of our 250 should be at risk. All right. So now imagine that the school wants to implement a new program, right? But it only has enough funding for 20 students. What we want to do is find a new cutoff score that identifies the 20 students that are at the highest risk. So let's think about this with a little bit more depth, right? What this is saying is that 28 of our students should be at risk for developing depression, right? Because we have a school of 250 students. We know that 11.31%, or a proportion of 0.1131, should score a 77 or higher. So in a school of 28 adolescents between the age of 13 to 18, we would expect 28 of our students to be at risk. But the school district is saying that we only have money to treat 20 students. So what we need to do now is calculate a new RAD score. We need to calculate a new cutoff score. This is a score that's likely going to be higher than 77. So we need to compute this new cutoff score that a student in our school would have to get, right? To have to be at or higher than that score in order to qualify for the treatment that the school is paying for, right? So in other words, because we only have enough money to treat 20 students, we need to move the goalpost here, right? Again, remember, if we gave all 250 students the RADs, we predict 28 of them should score above 77, right? Which suggests a risk for developing depression. Well, if we only have money for an intervention for 20 students, how do we decide which 8 are not going to get treatment, right? I mean, to be quite frank, this sucks, right? And that's the real world for you, right? We can't just sort of be random about it, right? We can't just, or I should say arbitrary and say, well, tough luck, 8 of you kids, we're just going to sort of pick 8 of you that don't get any treatment and wish you all the best. Well, no, we don't want to be biased here, right? We don't want to introduce the possibility of bias. So the solution is to create a new cutoff score that accounts for the fact that we only have enough money for 20 students. Well, how do we do that? Well, not surprisingly, there's math involved, right? We're not just going to arbitrarily create a new cutoff score off the top of our head, right? So this is going to involve a few steps here, right? And really the sort of thing that we're trying to do here is kind of solve for x, right? We know our sample size is 250, right? And we know how many students we have the budget to treat, which is 20, right? So we need to find, not find a new proportion that's equal to treating 20 students out of 250, right? So like I said, we need to find x. Well, how would we do that? Well, 250 times x is going to equal 20, right? X in this case is finding a new proportion, right? Our proportion from before was 0.1138, but that proportion is going to allow us to treat 28 students. We only have the money to treat 20, so we need to find the new proportion that will give us that will equal being able to treat 20 students. So what you do if you're trying to solve x for, in a sense, a multiplication problem, you want to isolate x to one side of your equation. In this case, you can do that by dividing both sides, in this case, by 250, right? 250x divided by 250 will cancel these out, and then you're left with x equals 20 divided by 250. You're left with x equals 0.08. So that's the proportion. That's the proportion of our students to equal being able to treat 20 students. So now we have this proportion associated with treating 20 students, right, which is 0.080. Remember, I told you we can look up proportions in our unit normal table, and we can find corresponding z-scores associated with those proportions. So we're going to need to look up this value of 0.08, right, in our unit normal table, and we're going to find the z-score that's associated with what's going to be our new cutoff score. But what we need to figure out is what part of the distribution are we looking up this proportion of 0.0800, right? Are we looking in the body? Are we looking in the tail? Or are we looking at mean to z? Okay, so let's think about this logically. And let's go back several steps. Should go back to this whole idea right here, right? Here we found, using finding the cutoff score, for the z-score for a cutoff score of 77, we were looking for the proportion at or above this particular cutoff score. And it turned out that that proportion was 0.1131. Well, now our new proportion, right? Our new proportion is 0.0800, right? So we're trying to identify some z-score that we don't know yet, right? But whenever we identify it, we know whatever that value is, the proportion associated with that, that represents that score or above, right? The proportion at or above whatever that z-score is, that proportion is going to be 0.0800. So it should make sense that the place that we want to look is in the tail, right? And what we're looking for is the proportion of scores that comes close to 0.080 without going over in the table. And when we find that, it's actually 0.0793, and we see it's associated with a z-score of 1.41. So a z-score of 1.41, the proportion of scores at or above a z-score of 1.41 is approximately 0.0800. So now we know the z-score that's associated with what's going to be our new cutoff, and now we need to find our new cutoff score. And the way we would do that is we would go back to an equation that we learned in Chapter 5. That equation allowed us to find a raw score, right, when we knew the population mean, the population standard deviation, and the z-score. And we know all those things, right? We know the population mean for the RADS is 60. We know the population standard deviation is 14. And we just found the z-score for what's going to be our new cutoff score. So we can insert all of that into our equation, right? Mean plus z times the standard deviation. So if I insert those things, I get a score of 79.74. Again, it sort of makes sense to round up in this case. So our new cutoff score is going to be 80, right? So given the fact that we can only treat 20 students, instead of using a cutoff score of 77 or higher, we've now figured out that the correct cutoff score to use is a score of 80 or higher. So out of our 250 students, anybody that gets 80 or higher is at risk for depression, and they would then qualify for our intervention. But we also know, based on probabilities, that should be 20 students, which is perfect because that's what we have the money to teach. All right. So now is the point where I would ask if there's any questions. Just as a reminder, z-scores and percents and other values should always be reported out to 2 decimal places, but don't forget when you're reporting probabilities or proportions, you should always report out to 4 decimal places. All right, so now we're going to find some specific probabilities, find probabilities for specific X scores, right? So here we're going to be transforming a raw score into a z-score, and we're going to be doing this for 2 raw scores and finding the proportion between those 2 raw scores. So this is a little bit trickier. And this is a very elaborate example of one of the questions that you have on the homework. So let's say we have this data, right? A highway department conducted a study measuring speeds on a highway. And the average speed they reported was 58 with a standard deviation of 10 miles per hour, right? So the average speed on this highway was 58 miles per hour, over a specific period of time with a standard deviation of 10 miles per hour. And they reported that the distribution for these data was approximately normal, right? Which is good, fine. So we want to find the proportion of people, in this case, who are driving between 50 and 60 miles per hour, right? Well, how might we do this? How might we figure out this problem? Well, in order to solve this problem, what we need to do is start off by computing the z-scores for 50 and 60 miles per hour. So we need to compute 2 z-scores here, right? We need to go 50 minus 58, whatever that is, divided by 10. And then we need to take 60 minus 58, and whatever that is, divided by 10. So that's going to give us 2 z-scores. So when we do that, right, we get a z-score for people traveling 50 miles per hour of negative 0.80, and we get a z-score of people traveling 60 miles an hour to be a z-score of plus 0.20. And remember, the question is asking us to find the proportion of people traveling between 50 and 60 miles an hour. So the next thing we want to do is draw a normal distribution and plot where those z-scores are and label them, right? Which is what I've done right here. And so again, the problem is asking us to find the proportion of people traveling between these 2 values, right? And again, so a z-score of negative 0.80 corresponds to 50 miles an hour. A z-score plus 2.0 corresponds to 60 miles an hour. So how do you think we might do this? Think about it for a second. Pause the video. When you come back, I'll talk you through it. Okay, so obviously we're going to need to look up some values associated with these z-scores in our unit normal table. The question is, what are those values, and how might we figure out the proportion between these 2 scores? Well, we could break this into 2, right? If we found the proportion of scores between mean and negative 0.80, if we also found the proportion of scores between the mean and plus 0.20, surely we could add these 2 proportions up to get the total proportion that falls between these 2 scores. So in this case, right, we're looking for the proportion of scores in both cases that fall between mean to z for a z-score of 0.80 and a z-score of 0.20, and then we're going to sum those together, right? And when we look those values up in our table, right? We find the proportion of scores between negative 0.80 to 0 is 0.2881, and the proportion of scores that fall between 0 and plus 0.20 is 0.0793. If we sum them up, right, we get a proportion of 0.3674. So in both cases, right, we'd want to find the z-scores. Remember, one of them was negative, but we're dealing with an absolute value because we said it was a symmetrical distribution. We would find the proportion between mean and z, right? So we get two different proportions. And if we sum them up, we get a proportion of 0.3674. And that's what the problem was asking us to do. We can also sort of give an interpretation. Remember, if this was a homework, we would end right here, right? This would be the answer, 0.3674. Here, I'm just sort of thinking about what it means in the real world. We can interpret this proportion as saying, well, about 37% of the cars were clocked at 50 to 60 miles per hour. But again, let me go back to the original question. It's asking what proportion of people were driving between 50 and 60 miles per hour. So the answer to the question, if it was a homework question, wouldn't be 37%. It would be 0.3674. It would be the proportion reported out to 4 decimal places. Okay. What proportion of people were driving between 70 and 80 miles per hour? Now, I showed you how to do one already. Let's see if you can figure out how to do one on your own. So I want you to find the proportion of people driving between 70 and 80 miles an hour. So it's going to involve computing 2 z-scores. It's going to involve drawing a normal distribution. It's going to involve plotting your 2 z-scores. And then you have to figure out, okay, what proportion falls between 2 scores? What and where do I look in my unit normal table and then figure out how to do that? Okay. So figuring out the z-scores is trivial, right? We need to figure out the z-scores for 70 and 80 miles an hour respectively. So let's start with 70 miles an hour. We're going to go 70 minus the mean of 58, which is 12. If we divide that by 10, we get a z-score of plus 1.20. Same process for figuring out the proportion of scores that fall between, for a raw score of 80. We're going to go 80 minus 58, which is 22. Divide that by 2. And we get a z-score of plus 2.20. So the next thing we want to do is plot those scores on a normal distribution, right? So here's roughly where a z-score of plus 1.20 is. Here's roughly where a z-score of plus 2.20 is. And we want to find the proportion that falls between these 2 z-scores, which correspond, remember, to a score of 70 and 80 miles an hour, respectively. Well, there are a couple of different ways you can do this. However you choose to do it, you want to make sure that you're consistent. The way I'm choosing to do it here is to find the proportion of scores that fall at or above plus 1.20, right, which is going to be from here all the way to the end of the distribution. I'm also wanting to find the proportion of scores that fall at or above plus 2.20, so that's going to be everything that falls from here to the end of the distribution. And here's the trick. If I find those 2 proportions, I'm going to be looking in the tail column here, obviously. If I find those 2 proportions, and if I subtract this one, which is the smaller of the proportions, from this one, which is the largest of the proportions, I cancel out these areas, and I'm left only with the proportion that falls between these 2 values. Again, you could have done this by looking in the body, right? You could have found everything that falls at or below plus 2.20. You could have found everything that falls at or below plus 1.20. And you still could have done the subtraction method, right? The key is, and you could have even done it mean to z, right? You could have found mean to z for here, mean to z for here, and still subtracted the smaller proportion from the larger proportion. The thing that I want you to really understand is that whether you choose to look for both proportions in the tail, or whether you choose to look for both proportions in the body, or whether you choose to look for both proportions in mean to z, whatever it is, you want to look for those proportions in the same area for both of your z-scores. So in other words, you wouldn't want to find the proportion of scores at or above 2.20 by looking in the tail, and then finding the proportion of scores that fall at or below 1.20 by looking in the body. If you look in the tail for one, then you want to look in the tail for other, and do the subtraction method. If you look in the body for one, then you want to look at the proportion of scores that fall in the body for the other score, and still do the same subtraction method, right? So if I look up in my table, right, the proportion of scores that fall in the tail for a z-score for 1.20, that's going to give me the proportion at or above everything for 1.20. I get a proportion of 0.1151. If I find the proportion in the tail for 2.20, so in other words, what proportion falls at or above 2.20, I get a proportion of 0.0139. And if I subtract those values, right, I get a total proportion, right, and I found them in the tail. If I subtract the smallest one for the largest, I get a proportion of 0.1012. So the proportion of scores that fall in this area, right, between these two z-scores is 0.1012. And again, the problem is asking us to find the proportion. I'm just sort of adding this as kind of a thought experiment, if you will, in terms of sort of what it means in the real world. And what it means is that given that distribution that these data came from, about 10% of the cars clocked by the traffic cam were traveling between 70 and 80 miles per hour. Let's just do one more. Right now we're looking at the proportion of people driving between 45 and 50 miles per hour. So again, pause the video. I'll give you a hint. Everything that we just did for the previous example of 70 to 80 miles an hour, we're going to do the exact same thing, except now we're looking at the proportion that we're traveling between 45 and 50 miles per hour. So pause the video, try and figure it out on your own, and when you come back, I'll give you the answer. Okay, so we're going to figure out a z-score for 45 and 50, right? So let's start with 45. We're going to go 45 minus 58. That's going to be 13, or negative 13 divided by 10. That's going to give us a z-score for 45 miles an hour of negative 1.30. We do the same thing for 50, right? We take that raw score minus the mean divided by the standard deviation. So that's going to give us negative 8 divided by 10. So that's going to give us a z-score of negative 0.80. And here I've plotted them, right? Here's negative 0.80. This is the z-score for a speed limit of 50. Negative 1.30 is the z-score for a speed limit of 45. And what we're trying to do is determine the proportion of people that were traveling between these two speeds. And again, I typically, look in the tail, right? So I'm going to find the proportion of scores that fall at or below negative 0.80, and that's going to be this area of scores in the tail. I'm also going to find the proportion of scores that fall at or below negative 1.30. So I'm going to look for that in the tail. So that'll give me all this area. And again, if I subtract this proportion out of this proportion, I'm left only with the proportion of scores that fall between the two values that I'm looking for. And again, if I look them up in the table, these are the proportions that I get. So remember, I would subtract the smaller value out of the larger value, and I get a proportion of 0.1151. So again, looking in the tail for these two particular z-scores. And remember, even though these scores are negative, because we're dealing with a normal distribution, it's symmetrical, so we treat them as absolute values. So I am looking for 1.30 and 0.80, right? And finding the corresponding values. If I subtract them, it's 0.1151. And again, just thinking about this in terms of what it means in the real world, about 12% of all cars were clocked going 45 to 50 miles per hour. We can also find z-scores that correspond with a specific probability. So that involves something that we did when we were doing the RADS problem, right? Where we found, well, okay, our new probability that reflects our new cutoff score is 0.80. We found that value in the tail of our distribution, right? We were looking for a value as close to 0.0800 without going over, and we found the corresponding z-score for that probability. We're going to do a little bit more of that here. But before we get into it, I just want to remind you again about the idea of the symmetrical nature of a normal distribution, right? Remember that between 0 and +1 standard deviation, 34.1% of all of our scores should fall. That's also true for the percentage of scores that should fall between 0 and -1 standard deviation. So this is a symmetrical distribution. So here we're asking what z-score separates the top 25% from the remainder of the distribution. So we're asking what z-score separates, what z-score would leave 25% to the right of it and 75% to the left of it. And how do we figure this out? Well, we draw a normal distribution and we approximate exactly where we might think that whatever z-score it is we're trying to find would be at the sort of 25% mark of the distribution, right? So here we draw our normal curve, and I'm going to use this one as an example because it's got all these percentages sort of factored in here. And I don't know, here's what I think it might be, right? I think if I were to draw a line, right, if I'm trying to find what z-score separates the top 25% from the remainder of the distribution, if I were to draw a line through a normal distribution, knowing these percentages here, I figure, well, 2.15 represents 2 and above, 13.6 represents 1 to 2, and wherever my mark is going to be here that represents the cutoff with 25% to one side and 75% of the other, looks like it's likely going to fall somewhere between a z-score of 0 and plus 1.00. I don't know what it is yet. And I'm sort of guesstimating here, but I think, well, it might be somewhere around here. Okay, it might be somewhere around here. Now, if I want to find the exact score, right, the exact z-score that separates 25% of the remainder of the distribution, well, I could convert 25% to a proportion, right, 0.2500. And if I know that 0.2500 proportion is going to be at or above this, right, because 25% falls to the right of the distribution, then I could convert that percentage into a proportion and try and find the value in the tail that's closest to 0.2500 without going over in the tail, which I've done here. And then I can find the corresponding z-score that's associated with that value. And it turns out that z-score, the z-score that represents this area of the curve that separates 25% from 75%, turns out that z-score is plus 0.68, right? So I could label that here. So roughly a z-score of 0.68 is the mark in a distribution that separates the top 25% from the bottom 25%. Okay, that's pretty easy. Let's try something that's a little bit more complicated. What z-scores form the boundaries of the middle 40% of all scores? So again, let's start with a normal distribution here. If I'm looking for the middle 40%, because this distribution is symmetrical, what I'm trying to figure out is, okay, where would I mark 20% from mean to the right side and 20% from mean to the left side, right? And that would equal 40%. Again, I know that 34% of all of my scores fall between 0 and plus 1, and 34% of all of my scores fall from 0 to -1. So I don't know, I'm guessing 0 to 20% is over here, and 0 to 20% is over here. And if I were to add up those two percentages, I would get 40, right? I would get 40. So now I'm trying to find what the exact z-scores would be, right? And this is pretty easy, right? I'm looking for the z-score in the mean to z column, right? That's as close as possible to 0.2000 without going over. And that's going to give me my z-score for mean to plus whatever it is, right? Plus whatever it is a technical term. So I'm looking for the closest value to 0.200 in the mean to z column without going over. That's 0.1985. And if I then find the z-score associated with that, that's 0.52, right? So the z-score between mean and the closest value to 0.2000 without going over, we established is plus 0.52. Well, now the other question is, because I'm looking for the middle 40%, that's only giving me 20%, right? It's giving me the mean to 20% for a positive z-score. If I want to find the two z-scores that form the boundary of the middle 40%, what do y'all think this z-score would be? Remember, it's a normal distribution, so it's symmetrical. If the z-score in the positive direction was 0.52, the z-score in the negative direction should simply be negative 0.52, right? So the two z-scores that form the boundary of the middle 40% is a z-score of negative 0.52 and a z-score of plus 0.52. And 40% of all of our scores fall between those two z-scores. Now, we might want to find an x scores that correspond to a specific probability from some distribution. And let's return to our SAT examples, right, where we had a mean of 500 and a standard deviation of 100. And we're asking here, well, what is the minimum score necessary to be in the top 5% of the SAT? And again, we're going to be doing something very similar to what we did in the RADS example. We're going to be doing something very similar to what we did when we were finding the z-score that separated the top 25 from the bottom 75% of the distribution. Except now, what we're trying to do is find the z-score that separates the top 5 from the bottom 95, right? So we're going to find a z-score for that. And we're going to use our formula that we learned in chapter 5 that allowed us to find our raw score if we knew the z-score, if we knew the population mean, and if we knew the population standard deviation. But first we need to start off by finding out, okay, what is this z-score that separates the top 5% from the bottom 95%? And I don't know, if I was plotting this on a normal curve, I think maybe this is a pretty good location, right? Like whatever this is probably the z-score that separates the top 5% from the bottom 95% of the distribution. And so what I'm looking at here, I want to find in the tail the proportion of scores that represent the top 5%. So I'd start off by converting 5% to a proportion, which is 0.0500. And I'm going to look in the tail for the z-score, I'm going to look in the tail for the proportion closest to 0.0500 without going over, and then I'm going to find that corresponding z-score. And the closest in the tail, without going over, is 0.0495. The corresponding z-score in this case is 1.65. And let's go back to our sketch here. We should also note that that's going to be plus 1.65, right? Because it's going to be on the right side of the distribution. It's the z-score that separates the top 5% from the bottom 95% of the distribution. So that z-score is going to be plus 1.65. And remember, as I told you prior to this, if we know the z-score, if we know the population standard deviation, and if we know the mean, right, then we can find what that raw score is. And let me just go back a couple slides. Remember, it's asking what is the minimum SAT score that you have to be in the top 5% of the SAT distribution. Well, now that we have the z-score associated with the top 5% of the distribution, we can plug that into our equation using this mean and using this standard deviation. So to be specific, we're going to plug it into this equation right here on the bottom, right? So we've got a mean of 500, a standard deviation of 100, and a z-score of 1.65. So we're going to go 500 plus 1.65 times 100. And that's going to give us a raw score of 665. So if we were to plot that on a distribution, right, we'd see that anybody that gets a 665 or better is in the top 5% of the SAT distribution. Okay, great. Let's get it, do one final example, just a little bit more difficult here. And let's ask, what is the range of scores that correspond to the middle 50% of all SAT scores? And this is going to be similar to when we found the two z-scores for our middle 40% of the distribution, except now we're looking for the middle 50% of our distribution, right? So 25% to the right, 25% to the left. And we're still looking up z-scores here, right? So we can convert that 25% to the right to be 0.2500, and we're looking from mean to z, right? Mean to z. And remember, we're going to get two z-scores here. They're both going to be the same value, except one is going to be positive and one is going to be negative, right? This value is going to be positive. This value is going to be negative. And so we're looking up the value in the mean to z column for 0.2500. We're looking up the closest value without going over. Turns out that's 0.2486. So the z-scores associated with that are going to be plus 0.67 and negative 0.67. And remember, the question is asking us to find the range of scores, not z-scores, but the range of SAT scores that correspond to the middle 50% of the distribution. So now we need to do that formula that allows us to find the raw score, but we need to do it for a z-score of negative 0.67 and a z-score of plus 0.67. And here's the math on it, right? So for the z-score at the low end of the distribution, the raw score for that's going to be 433, and we're going to figure that out by taking 500, adding it to negative 0.67, and multiplying that by the standard deviation. So that gives us 433. We do the same thing for the z-score of plus 0.67. That's going to give us a SAT score of 567. So when we plot it, we see the range of scores on the SAT that correspond to the middle 50% of the distribution fall between 433 and 567. Okay. That's it. This is again the point in time where I would ask if you have any questions. Here, you know everything that you need to know to do the homework. And you know, if you're looking at the syllabus, you'll note that even though I've recorded this lecture all in one shot, you know, I would suggest listening to this lecture over the span of 2 days, because it is a little bit longer. So there you have it. So again, if you have any questions, be sure to let me know.